Yes, you can install two conductors on the secondary of a transformer and then feed separate disconnects. Consider a 75 kV ampere 480-243 phase 3-wire transformer with number 3 conductors on the secondary. You can connect two number 3 conductors to the transformer's secondary lugs and run them to separate 100 amps fusible disconnects. Each disconnect will be fed by a number 3 conductor in 1-inch electrical metallic tubing. This practice aligns with the National Electrical Code. Now let's delve deeper into the relevant sections of the National Electrical Code, specifically focusing on equipment grounding, conductor continuity, and conductors in parallel. Firstly, regarding equipment grounding, conductor continuity, Section 240.21. B1 of the National Electrical Code emphasizes that the equipment grounding conductor must be continuous throughout the entire grounding system. Conductors designated for grounding should not be utilized for any other purpose. This ensures a dedicated path for fault current, enhancing safety and minimizing the risk of electrical shock. Secondly, concerning conductors in parallel, Section 310.15. B4 addresses scenarios where conductors are used in parallel as permitted in 310.10. H. This section mandates that all parallel conductors must have the same length and comply with the provisions outlined in 300.3. B. The ampacity of any conductor used in parallel must be equal to or greater than the ampacity of the individual conductors within the group. Table 310.15. B4 specifies how the length of parallel conductors should be determined based on the conditions of use. In addition to National Electrical Code references, there are several additional considerations to keep in mind. The lugs on both the transformer and the disconnects must be explicitly rated for accepting two conductors. This ensures a secure and reliable connection. The conductors themselves must be sized appropriately, taking into account both the load they will carry and the distance to the disconnects. Proper sizing prevents overheating and voltage drop. The disconnects must be adequately sized for the conductors connected to them and the load they are intended to serve. This ensures the disconnects can safely interrupt the circuit under normal and fault conditions. Finally, all aspects of grounding and bonding must be installed correctly, adhering to the relevant National Electrical Code requirements. Proper grounding and bonding are crucial for minimizing the risk of electrical shock and ensuring the safe operation of the electrical system. To elaborate further on conductor ampacity, it is essential to consult the ampacity tables provided in the National Electrical Code, specifically Table 310.16 and related tables. These tables provide the allowable ampacities for various conductor sizes and insulation types, taking into account factors such as ambient temperature and the number of current-carrying conductors in a raceway or cable. When selecting conductors for a particular application, it is crucial to ensure that their ampacity is sufficient to carry the expected load current continuously without exceeding their temperature rating. Overloading conductors can lead to overheating, insulation damage, and potentially fire hazards. In addition to ampacity, voltage drop is another critical consideration when sizing conductors. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is often necessary to increase the size of the conductors, especially for long runs. To reiterate, when selecting conductors, it is crucial to consider both ampacity and voltage drop to ensure the safe and efficient operation of the electrical system. The selection of appropriate disconnects is equally important. Disconnects serve as a means of isolating electrical circuits for maintenance or in the event of a fault. They must be properly sized to interrupt the maximum available fault current at their point of installation. The interrupting rating of a disconnect must be equal to or greater than the available fault current. Failure to select disconnects with an adequate interrupting rating can result in equipment damage, personal injury, or even death. Disconnects are available in various types, including fused disconnects and non-fused disconnects. Fused disconnects provide overcurrent protection in addition to isolation, while non-fused disconnects only provide isolation. The choice between fused and non-fused disconnects depends on the specific application and the need for overcurrent protection. In many cases, fused disconnects are preferred because they offer both isolation and overcurrent protection in a single device. Proper grounding and bonding are essential for electrical safety. Grounding refers to connecting the electrical system to the earth, providing a low impedance path for fault current to flow back to the source. Bonding refers to connecting all metal parts of the electrical system together to create an electrically continuous path. Proper grounding and bonding minimize the risk of electrical shock by ensuring that fault currents are quickly cleared, tripping circuit breakers or blowing fuses. The National Electrical Code provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods of connecting grounding conductors to equipment, and the requirements for bonding metal parts of the electrical system. It is crucial to follow these requirements carefully to ensure a safe and reliable electrical system. The equipment grounding conductor plays a vital role in the grounding system. It provides a path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. The equipment grounding conductor must be sized according to the requirements of the National Electrical Code, based on the size of the circuit conductors. It must also be properly connected to all metal parts of the electrical system, including equipment enclosures, raceways, and junction boxes. In addition to the equipment grounding conductor, the grounding electrode conductor connects the grounding system to the earth. The grounding electrode conductor must be connected to a suitable grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. The size of the grounding electrode conductor is also determined by the requirements of the National Electrical Code, based on the size of the service entrance conductors. The bonding of metal parts of the electrical system is equally important. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. Bonding is typically achieved by connecting metal parts together with bonding jumpers or bonding screws. The National Electrical Code provides specific requirements for bonding various types of metal parts, including equipment enclosures, raceways, junction boxes, and metal water pipes. Now let's talk more about transformers. Transformers are electrical devices that transfer electrical energy from one circuit to another through electromagnetic induction. They are commonly used to step up or step down voltage levels to match the requirements of different equipment or systems. Transformers consist of two or more coils of wire, called windings, wound around a common core. The primary winding is connected to the source of electrical energy, while the secondary winding is connected to the load. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. For example, a transformer with twice as many turns in the secondary winding as in the primary winding will step up the voltage by a factor of 2. Transformers are available in a wide range of sizes and types depending on their application. Small transformers are commonly used in electronic devices, while large transformers are used in power transmission and distribution systems. Transformers can be classified as either step-up transformers or step-down transformers depending on whether they increase or decrease the voltage level. They can also be classified as either single-phase transformers or three-phase transformers depending on the number of phases of the electrical system they are used in. The 75 kV ampere transformer mentioned earlier is a three-phase transformer, meaning that it is designed to be used in a three-phase electrical system. Three-phase power is commonly used in commercial and industrial applications because it is more efficient than single-phase power. The primary voltage of the transformer is 480 volts, while the secondary voltage is 240 volts. This means that the transformer steps down the voltage from 480 volts to 240 volts. The transformer is also described as being a three-wire transformer, meaning that it has three conductors on the secondary side. The three conductors are typically labeled A, B, and C. The voltage between any two of these conductors is 240 volts. The National Electrical Code provides detailed requirements for the installation and wiring of transformers. These requirements cover a wide range of topics, including transformer overcurrent protection, transformer grounding, and transformer ventilation. It is crucial to follow these requirements carefully to ensure the safe and reliable operation of the transformer. Overcurrent protection is essential for protecting transformers from damage due to overloads or short circuits. Overcurrent protection is typically provided by fuses or circuit breakers installed in the primary and secondary circuits of the transformer. The size of the overcurrent protection devices must be carefully selected to protect the transformer without causing nuisance tripping. The National Electrical Code provides specific requirements for sizing overcurrent protection devices for transformers. Grounding is also essential for protecting transformers and the electrical system from electrical shock. Transformers must be properly grounded according to the requirements of the National Electrical Code. Grounding is typically achieved by connecting the transformer case and the neutral point of the secondary winding to a grounding electrode. Ventilation is also important for preventing transformers from overheating. Transformers generate heat during operation, and if they are not properly ventilated, they can overheat and fail. The National Electrical Code provides requirements for transformer ventilation, including the minimum amount of free airspace required around the transformer. Let's recap. Connecting two conductors on the secondary side of a transformer to feed separate disconnects is a common and acceptable practice, provided that certain conditions are met. The lugs on the transformer and disconnects must be rated for two conductors. The conductors must be properly sized for the load and distance to the disconnects. The disconnects must be properly sized for the conductors and load. All grounding and bonding must be properly installed. The National Electrical Code provides detailed requirements for the installation and wiring of transformers and disconnects. It is crucial to follow these requirements carefully to ensure the safe and reliable operation of the electrical system.